Good morning to all the participants. Today we are handling with the strength of material class, 18th class. Thank you very much for all to giving me an opportunity to speak to you about the subject. Now till now we have discussed the stress strain diagrams, stress strain, simple stresses and strains, geometrical properties of sections, and bending moment and shear flow diagrams. We have discussed elaborately in length. Now today I am discussing with the bending stresses in beams. Stresses in beams. The engineers, maybe civil engineer or mechanical engineer, one should know the behavior of the beam. One should understand the beam. Now in regular practice, we build the structures like buildings, multi-story complexes, buildings, then bridges. So many structures we are designing and building. They are all operative. They are all right. So the beams are more critical element, load resisting element. Now, for example, if you come across with the bridges, railway bridges across the rivers, the beam span length sometimes 60 meters, 20 meters, 40 meters, depending upon the circumstances and the technology available, the material. Now the engineer has to decide. Now how the engineer has to decide? He should know the concept. He should understand the behavior of the beam. Now this is the fundamental subject, that is strength of materials. The engineer must know about this thoroughly. Then we can decide what should be the size of the beam, what should be the material being used, and what should be the breadth and depth of the beam. Now before saying this, we should understand clearly the behavior of the beam, depending upon the load condition. The main thing, the important features. One feature is the load, how the beam is loaded. The most important feature is beam load on the beam. The other important feature is the span. Now these two are the more critical. If you are able to understand this, depending upon the span, length of the beam span, length of the beam, and the load acting on the beam. If you are capable of understanding this, now due to this, how the beam behaves. Now normally when we are applying the load, it tends to drop. When you drop the load, the end product of the load is deformation. End product of the load is bending. End product of the load is deflection. Now when you drop the load, it should fall. Now what we are doing now, being engineers, now we are not allowing the load to come down. Therefore we need to provide a structure, a beam structure, maybe a column structure, whatever may be, depending upon the circumstances. Now let us understand clearly the behavior of the beam, how the beam behaves. Load applied load. Now if the load increases, the deformation, bending increases. Now there is a critical issue to be addressed. One should understand this. When the load is increased, it deforms. It is deformed, deflection will be more. Now, suppose if the span is more, the deformation will be more. So therefore, we need to provide the section. We need to provide the beam, design the beam in such a way that the load should be resisted by what column. This should not be the result. The result should be like this. Whatever may be the load, what type of load, whatever may be the material, whatever may be. Now we must be very careful while understanding this. Now we are addressing this. We are addressing this in this chapter. Now that is called theory of bending. Theory of bending stresses. How the stresses are induced due to this load, the bending. Now that is the main theme of this subject. Now if you understand the behavior of the beam, now we are able to. We don't know that if we are not able to understand the behavior of the beam, not possible to design the beam. So the engineer has to play with the load, and the span and the section and the depth and breadth. To decide what should be the breadth and what should be the width and what should be the depth and what should be the span. Everything depends upon the necessity. The necessity span depends upon the necessity, and the span depends upon the material available and the site conditions. Now, whereas the load again, it depends upon why the structure has been built. Now, therefore, now let us understand clearly one by one. Now, please understand the beam. A beam has the length and support. That is support, the length and the section. So, for example, I have taken one. I have that is I have taken this. The wooden beam. The wooden beam has length L, and here the sectional property is also more important. We have discussed about this in length in the previous chapters. The geometrical property, the one should understand the geometrical property too. Now therefore, that is sectional property. It is section. Section is B and D, breadth B and depth D. This is the section, cross-sectional property. And this is the one beam. I have taken the live example. It is a wooden beam, isn't it? And now in the previous case, the beam is loaded with uniformly distributed load, and in this case, the beam is loaded with the point load. Point load, any number, and also point load, etc. Whatever may be, the end product is only the deformation. Now we have to minimize the deformation. Or no deformation should occur in our structures. Whenever we apply the load on the beams, so what is going to happen? Now this is the deflection. Now this deformation takes place. Now this deformation. Now how we will know? There are so many methods. There are so many ways to find out what is the deformation, what is the deflection. Now the most important here, the moment, bending moment. The moment. Now what is the moment? That is rotation. That is deflection. The rotation. Now we need to understand how much how this behaves. Now how the beam has to be designed. And now due to this, the moment, whenever you apply the force, there will be a moment. Now this deforms in this form, in this shape. Now this is the beam will deform in this way. Now therefore, whenever we apply the force, load, when the load is applied, the bending, it is called bending, the bending moment. Isn't it? Now already we have discussed about this bending moment in the previous chapter in length. Now this is the bending and the deformation take place in this way. And now in the bending theory, there are some assumptions in the beam. There are some assumptions. Now the assumptions. Now when in our strength of material, the material of the beam is perfectly homogeneous and isotropic. The material of the beam is perfectly homogeneous and isotropic. Now that is the material is uniform all over the all along the beam, and you know all along the beam, and the load distribution is uniform all throughout the beam. Now that is the assumption. Now strictly speaking, it is the assumption the material of the beam is perfectly homogeneous and isotropic. And again, the another assumption, the beam material is stressed within the elastic limit and obeys the Hooke's law. Now, what Hooke's law says? Stress is proportional to strain. Now, you see, in our engineering practice, all the load resisting elements are working within the elastic limit. When working within the elastic limit, now suppose till then, that limit, the body regains its original position after removal of the load applied. Now, after removal, otherwise what happens if you are continue the application of load further, the deformation increases, and beyond the elastic limit, the body will get into plastic state, isn't it? Till then, it is assumed that the beam material is stressed. Now it is working within the. Till then, our theory is good. Now beyond that, the body will rupture, or it will go to gets into plastic state. When it gets into plastic state means that is the body will not come back to its original position. Not after the beyond that the limit, isn't it? Now there are many more assumptions. The one is the material of the beam is perfectly homogeneous and isotropic. The second one, the another one is the beam material is stressed within the elastic limit and obeys the Hooke's law. And this is the beam. Now we have assumed. Now this is the beam uniform section, and uniform material is homogeneous and isotropic. Now in practice, sometimes, strictly speaking, it may not be true in the practice, but theory is always holds good, isn't it? Without theory, we are not able to design this beam. But in practice, in construction practice, there may be some error in construction activity. Therefore, sometimes there may not be uniform. There may be some error. Still, our theory is definitely holds good for the design of to understand or to design of this beam, isn't it? So this is one concrete beam I have taken from the side. And this is not. Sometimes there may not be uniform, but one example I have shown. But theory assumptions are true. Whatever the assumptions we have made, it is right, isn't it? It is essential for our design purpose, isn't it? Next. And the another assumption, that is each layer of the beam, the beam assumption, the beam is it is assumed that the beam is made out of number of layers. The number of layers, the beam is made out of number of layers. It is an assumption. In each member, when the load is applied, each member, when you apply the load on the beam, now what is going to the bending moment occurs, isn't it? When bending moment occurs, this is the bending shape of the beam. Now this is the bending shape of the beam. No, it is the assumption. What is the assumption? The beam is made up of number of layers. Number of layers, when there are many number of layers, made out of many number of layers, isn't it? Now here, when the deformation takes place, now see here, see this is the made out of number of layers. When the deformation, in this deformed section, the deformation takes place, these layers, now we have to understand the behavior of each layer. Now here each layer are independent. Now the layer 1, layer 2, layer 3, I have shown few layers here, and there are many number of layers. There are some. Now each layer in the beam, the layers may be 1, 2, 3, 4, 9, any number of layers. There are perpendicular to this section. There are many number of layers. Now each layer is independent to contract or to elongate, isn't it? The each member. Now first the assumption is the beam is made up of number of layers. It is BD number of layers. The beam material. The beam is made up of number of layers. Now each layer is independent. Is independent for to expand or to contract. Now when the beam is stressed, when the load is applied, the beam is stressed and it is a bending shape, isn't it? Now more than these layers, what happening now here in this layer? In this layer, now here, now see the top layers shorten. Top layers, the length of the layer at the top is compressed, and at the bottom of the layer is elongated. Now therefore, now see, when you look at this deformed shape of the beam, now the top layer is suffering from compression. That is the length of this layer reduced by the original length. It is less than the original length. This is the original length. If a portion is taken here, a beam portion is considered, and for this beam, in this beam portion, now this is delta x. The length of this is the delta x. Now here, now this the top layer is less than the top layer is less than the delta x. Now delta x you have considered here from here to here, a portion of the beam. Now this top layer is less than delta x, isn't it? Now that means that is compressed. The top layer is, the length of the top layer is reduced. Now then if you go a little beyond little below, when you reach below this, now what is going to happen here? That is this also the length of the next layer is also shortened, isn't it? It is less than delta x, isn't it? Now similarly, now if you go beyond this from here to here, now the next layer is again the length of the next layer is also the length of this next layer is also less than delta x. Now this is the length, this is the delta x is the one portion of the beam you have considered. Now here, now the beam, the layer, top layer is suffering from, that is shortening, isn't it? It is get shortened. It is less, the length is less than delta x. Now this is also less than delta x, and this layer is also less than delta x. This layer is also less than delta x. This layer is also less than delta x. But one thing we should observe here. Now here, now this is this length. Now this is elongated. This is compressed. The compression here, it is more than this, isn't it? Now let us assume that there is some deformation. Now this here, the length is little more than this, the top layer, little more than the top layer. Now this length is little more than this. This length is little more than this. Like, you know, see now what I mean to say here is, now see this is the delta x length. Now these layers, all these layers are less than the length, that is delta x, less than. Now among these layers above this central line, that is this central portion, central line, are all shortened by its original length. Its length, that is delta x. Now delta x above this layer, all these layers are less than the delta x. Now in that again, this is the maximum shortening takes place in this layer. Now it is little more than this. The length of this is little more than this one, and from here to here again there is a little more, more than that. Now that means what I mean to say. Now this is suffering maximum shortening, isn't it? The topmost layer is suffering from the maximum length, that is shortening. Now this is little less than this. This is little less than this. Like, you know, now when you read this, this RS, now there is one layer, this RS layer, R dash S dash RS layer. Now here RS layer remains the same length, isn't it? Now this now see here all the layers having same length. Now, whereas here the length decreases, isn't it? But this layer, now this layer, central layer, this layer is same length, isn't it? Now this is S, R and RS. This is RS layer. This layer is same. This length and this length are same. Now similarly, if you go down below this RS layer, now this is below this RS layer. Now this layer is length. This layer length is more than this. Now that means this layer is suffering from extension, isn't it? The length of the next layer is more than the original length. That is original length. That is RS length, isn't it? Now, if you go a little further again, now this layer is little more than the length of the next layer is little more than this. And similarly, now if you go further, now this layer is again more than this, isn't it? Like now the layers are suffering from, that is tension. Now below this layers, one layer RS, this is the layer, one layer. Now that layer depending upon the load condition and depending upon the material, depending upon the span. Now what I mean to say here is, now from this layer, above this layer, all these layers are suffering from compression, isn't it? That is the length of this reduced less than the original length, isn't it? Now below this layer, now all the lengths of all the layers are more than this length. Now that means now the layers below this line, below this central line RS, all the layers are suffering from tension, isn't it? That is the length of length of these layers are more than the original length, isn't it? RS. So the RS is the length of the section where beam section we have considered, and from all the above layers are, now here all the layers are same length. Now after loading, now when the deformation takes place, now this is the behavior of the beam. No one should understand this, isn't it? When we know that since from the beginning we are discussing about the strength of material, now we are discussing, that means when there is a shortening, when the load is applied, there is shortening, that means stress is induced, isn't it? Now here also, it is the member, this layer is suffering from compression. Therefore, the stress induced in this layer is, that is compressive stress, isn't it? Now the load applied. We have applied the load, and due to this load, that there is a shortening in the layer, in this layer. Now therefore, this layer is suffering from compression, isn't it? The length shortening. Now therefore this layer is suffering from, that is compressive stress, isn't it? And similarly, now this layer is also suffering from compressive stress. This layer is also suffering. Now it means, what I mean to say here, the above this RS, the layer, there is no change in length of this layer, that R-S layer. R-S layer, it is not suffering from either expansion or shortening. Now that is here above this layer, all these layers, this layer is suffering from compression. This layer is also suffering from compression. This layer is also suffering from compression. Now above this, all the layers are suffering from compression. Now whereas this layer, there is no expansion or there is no contraction. Therefore, this layer is not suffering from any, that is expansion or contraction. Therefore, there is no stress is induced in this layer, isn't it? Now if you come down little below, now here, this layer is expanded. That is, this is the length of length of the layer. This layer below this RS. Now this layer is this length. Now when you go down, when the load is applied, this is expanded, isn't it? When this is expanded, now when the load, when this layer expanded, now it means Now there is a stress induced in the material, is it not? In the layer, stress induced in the material, and this stress is tensile stress. Now the stress is induced against tension, that is tensile strain. Now that is tensile stress. Now similarly, this is also suffering from tensile stress because it is more than the length of this is more than this. When the load is applied, this expands, this layer expands, this layer is also expand. This layer is also, see, all the layers below this, no, R dash, S dash, isn't it? Now what I mean to say now here, see, now this is the beam loaded, there is a bending moment induced in the beam. Now when the bending moment is induced, there is a deflected shape of the beam, deflected shape. Now this beam deflects in this param. Now when deflects in this param, now here length of all the layers are same here. After deflection, now this one layer length remains same. Now above these layers, all the layers are suffering from compression. Is it not? All the layers above this R dash and S dash are suffering from compression. Is it not? Now therefore, the stresses induced in all these layers, all the above layers above this R dash S dash is a compression zone. Now similarly, below this R dash S dash, below this, now what will happen? All the layers are expanded. Now therefore, the stresses induced in all these layers is tensile stress, isn't it? Now therefore, now what I mean to say now here, it is compressive stress in this layer, compressive stress little less, compressive stress little less, compressive stress little less. So like the compressive stress get reduced from top layer to the middle layer, this layer up to here, and after this from here to here, from below this, that is RS, that is original R dash S dash, original here RS is equal to R dash S dash, isn't it? Now that is the central layer. Now see, below this layer, all the layers are suffering from tension, isn't it? Now see, this is the tensile stress induced in this due to expansion. Now this is tensile stress is little more than this here, isn't it? Now compared to the previous layer. Now tensile stress is little more in this layer when compared to the previous layer. Like now you go down, when you go downward, that is below. Now the farthest, this layer is suffering from maximum compression, isn't it? Sorry, maximum tension, isn't it? Now what I would like to say here is, now this is suffering from maximum compression, this is suffering from maximum tension, and now see, this is compression, less compression, less. Now whereas here no compression or no tension, because there is no expansion or there is no compression. Now that means, now what is the stress induced in this? Therefore, the stress induced in this material, in this layer, is zero, isn't it? Now this is called zero stress axis, isn't it? It is called zero stress axis, and this we are calling this as neutral axis, isn't it? Now in this theory, bending theory, that is neutral axis. Neutral axis is nothing but not half of this, isn't it? The section, half of the section. It means that is, now here the stress is zero. That is, the stress is zero. That zero stress axis is called neutral axis, isn't it? We are calling this as neutral axis. Now once I will repeat again. Now see, we have taken this, the beam loaded, and I have considered one portion of the beam. Now this is delta x length, and this beam is made out of number of layers. 1, 2, 3, 4, 100,000 number of layers. When the load is applied, Now due to the load effect is deformation, that is deflection, isn't it? When it deflects, the maximum now the layer, one layer, it is zero expansion or zero contraction. That is original length. That is what is the length we have considered here. That is delta x. This length is also delta x. Now whereas here delta x minus 1, delta x minus 2, delta x minus 3, like now the length, that is length of all these layers get reduced, and this is suffering from maximum, that is compression, isn't it? Now it means to say that the farthest layer, the top layer, is suffering from compression, and farthest bottom layer is suffering from maximum tension, isn't it? Now therefore, and now maximum compression, less compression, less compared to this, less compared to this, less compared to this, and here no compression or no tension. Therefore, it is zero stress, isn't it? Now again, when you go down below, that is the length of the layer is the next layer is elongated. It is little more elongated, little more. Therefore, the farthest layer is suffering from maximum tension. Now this layer, now this is called zero stress axis layer. Now there is no expansion or there is no contraction. Now therefore no stresses are induced in this layer. Now therefore no stresses, because delta x, here also the delta x, length of this is here delta x, and here also delta x. Now whereas here delta x minus, isn't it? Delta x minus, isn't it? Previous. Now therefore this is suffering from maximum shortening. Therefore it is maximum suffering from maximum compressive stress. Now here also below this, now we will call straight away, that is neutral axis. That is neutral axis. Then now above neutral axis, all the layers are suffering from compression, isn't it? Farthest layer is suffering from maximum compression. Now whereas below this, the maximum below this, the neutral axis, below the neutral axis, all the layers are suffering from tension, isn't it? And the farthest, that is the last one, farthest, the farthest layer is suffering from tension, maximum tension, isn't it? Now this is the bending theory. This one, if you understand this, the rest we can solve this. And the assumptions, already we have discussed the assumptions. The assumptions. So the first assumption in there. Now the material of the beam is perfectly homogeneous and isotropic. The second one is the beam material is thrust within the elastic limit and obeys the Hooke's law. And the third one is each layer of the beam is free to expand or contract independently of the layer above or below. These are the assumptions, isn't it? And now here the another assumption we have made here. Now see the Young's modulus, where the value of the Young's modulus is same in tension and compression, isn't it? Whether it is tension or compression, the Young's modulus, the value of Young's modulus is same in tension and compression. There is no. This is also an assumption. The next one is, see, the transverse section. Transverse section is plane, which was plane before bending, will remain plane even after bending, isn't it? Now, if the transverse section is a cross section, now this is like this, isn't it? After bending, again it remains plane, isn't it? Now, this is the assumptions what we have made in the theory of simple bending, isn't it? One should understand clearly about this concept, then further. Now, we'll go back. Now here, see, now if you consider a beam, RCC beam, you can, if anybody can recognize, the bottom layers are suffering from maximum tension. Therefore, the steel is strong in tension. Therefore, in the beam, we provide the steel reinforcement at the bottom. We will provide the steel reinforcement at the bottom in the beam to resist the tensile force, because the steel is more stronger in resisting the compressive force, also the tensile force, isn't it? Whereas the concrete is strong in resisting the compressive force, therefore in the compression zone we provide the concrete, isn't it? Now that is the principle, that is from where our the design of beams starts, isn't it? Therefore one should understand clearly. Then from this we can derive, or from this we can design any kind of beam. The material may be anything, whatever may be. There may be steel, maybe steel beam, maybe concrete beam, maybe RCC beam, maybe wooden beam, whatever may be. The concept is same concept, isn't it? We have to follow this concept. Now it is suffering from the maximum tension. Therefore, we need to provide to resist the tension. We need to provide the steel in the upper zone, above the neutral axis. Above the neutral axis, it is a compressive zone. This is the tensile zone. Below this neutral axis, this zone is tensile zone, and this zone is compressive zone. Therefore, we need to take care of these compressive forces, the tensile forces, and we need to take care of the compressive forces. Therefore, now we are providing steel is strong in resisting the both compression and tension. Therefore, we are providing the steel at the bottom in the beam section of this kind, isn't it? And then in the compression zone, we are providing the concrete. Concrete is strong in resisting the compressive forces, isn't it? Next, please. Okay. Yes, the transverse section. Now here, the transverse section remains same. This is another assumption made in the theory of simple bending. Now, this theory, assumptions holds good and it is valid, and it is true in the theoretical part, and we have to we have accepted, and we have to carry out with this, and isn't it? No assumptions. Don't forget the assumptions. It is always holds good, and it is used in the design of all our column beams, isn't it? Next, please. Yeah. Now here in the theory of simple bending again. Now see, we have discussed this length. Now this is I told you that this is the neutral axis. Neutral axis means zero stress axis. Now it is zero stress axis. Now above layer, here the layers above this zero stress axis, neutral axis, are suffering from, that is, compression. Now below this neutral axis, it is suffering from, these are suffering from tension. See, now this is the beam. This is how we are going to design it. Now this is one rectangular beam, and this is the circular beam. Now for this, now see here. Now this is the circular beam. Now this is circular beam. Now that is rectangular beam, and this is one I section, and it is all over rectangular beam. Isn't it? The beam. Now here, it is symmetrical beams. These are all symmetrical beams. Now what happens? According to the stress calculation, according to this theory, stresses induced the maximum compressive stress at the topmost fiber and maximum tensile stress in the bottommost fiber, isn't it? Now therefore, see, now it is called stress diagram. It is called stress. This is the stress diagram. Stress diagram. Now you take one reference. Now, according to the computation, now this is suffering from maximum the compression. Therefore, you plot this compression, and below next layer, that is little less. Below this little less. Below this little less. Below this. Now it is the neutral axis. It is 0, and below this will come down. Now this is suffering from tension. Now this is suffering from tension. Now here the less tensile stress. No, it is more. Now it is increasing in this, isn't it? From zero to neutral axis to the bottommost fiber. Now this increases, isn't it? The stress. It is a variation of the stress diagram, isn't it? Bending stress diagram. Now it is the this is how we can plot. Now this is how we can plot. Now here above the neutral axis, not all the layers are suffering from compression, and this is the maximum compression, isn't it? Now similarly, now here again, now at the bottom, that is compression is maximum tension. Now this shows the variation of the bending stress across the section, beam section, isn't it? Now these are all symmetrical, the symmetrical sections. Now this is how the plot, isn't it? Now this is the shear, the bending stress diagram, isn't it? Stress diagram. This is called bending stress diagram. And see, if we consider, see, this is the normally what we are going to do it in practice. Now this is a rectangular beam. Now it is a circular beam. Now circular section, rectangular section, circular section, and I section. Now this is a hollow rectangular section. Now what I need to say here, the behavior. Now when you understand this behavior, now here it is suffering from maximum compression. Therefore, we need maximum section to resist. Isn't it? Now therefore here again, now this is we need section here to resist. Now here when you reach this point, now it is 0. Therefore, we don't want any section here. But the structure will not in existence. We need. Now therefore, what we are to do according to the stresses, now we are designing the section. Isn't it? Now one example. See this is the rectangular frame. This is the I section. Now what is the difference between this? What is the difference between this? This is the I section. Now this material is safe. Now this part of the material, this is the rectangular section, and this is the I section. Now this amount of material is saved, isn't it? Now for example, one best example is a rail. That is a rail track, isn't it? In the rail track, now see this amount of material we are saving. We are going to save this. Now this is called engineering. No, that is how we are and we are designing the section. Now again, in this case also, now here stress is more, we have more section here, isn't it? Stress is less here, now therefore less section here. Now stress is more here, that is tensile stress. Now we have provided the more section here. Now according to the stresses, now the section has been designed, isn't it? Now these are the regular sections, isn't it? Sometimes what happens, this is, sometimes there are in our regular construction practice, in our practice, we use the irregular sections. So these are the irregular sections. Now in irregular section, now the stress diagram is varies, isn't it? Now according to, depending upon the load, depending upon the section, the stress diagram varies. Sometimes this will be more, the compression will be more. Sometimes this tension will be more, and at that point of time the neutral axis shifts. Now it moves. Now depending upon the load condition, and the sectional properties, isn't it? One should know about all these things. All these things are being used in our regular construction practice, isn't it? Yeah, in theory of simple bending, now see the design. Now whatever the things we have discussed, now this is all these things are mentioned here. Now in our syllabus, in our Polytechnic students syllabus, derivation of this bending equation is not included, isn't it? Not in our syllabus. Now therefore, I will skip this portion. Now just the that is proof of our bending equation. How to derive the bending equation? Straight away I will go to the bending equation, isn't it? No proof part not included in our syllabus. Now therefore, the theory, whatever the things we have discussed, all these things are available and printed here. Whatever the things we have, so far we have discussed about this. See, I think neutral layer or neutral axis. Now we have discussed in length about all these things, isn't it? Next, please. Yeah. Now this is the bending equation. the bending equation. Now in bending equation, now one should know about, see, now this is the beam. Beam, load applied, when the load is applied, moment, that is bending moment, then deformation, deflection, isn't it? All these things, isn't it? Now you know, see, we have this, see, M is the bending moment, bending moment in kilonewton meter. We have discussed about this in our previous classes. Now, bending regarding how to calculate or plot the bending moment diagram, how to calculate the bending moment. Now, this M is the bending moment in kilonewton meter, and F is the stress in the layer, all this layer in the layer, isn't it? No one should understand here. Now, this is the neutral axis. Neutral axis, that is 0 reference. Now, when you reach this point, that is Y. Now, this is the farthest distance Y. Y is that is the fiber stress. Now, if you consider Y from here to here, the stress will be less. If you consider Y from here to here, it is little more than this. Now, if you go at the for the farthest last layer, the stress will be more. Now, therefore, now we are calling this as fiber stress. Sometimes some people will call fiber stress, and some will call skin stress, bending stress, whatever may be. And some people will use FB, that is F, that is suffix B. Now that means suffix B, that is bending stress. Now F normally we use, that is it is the abbreviation we use. It is F is the stress. Stress in the layer, each layer, isn't it? Now wherever you want to calculate, now you measure from here to here, no distance, no. But maximum stress is in the farthest layer. Therefore, usually we will take the last layer, isn't it? For the last we will calculate. Now F is the distance, and F is the stress, skin stress or fiber stress in newtons per millimeter square, and Y is the distance of the layer from the neutral axis in millimeter. Y is the distance from the neutral axis. From the neutral axis, Y may be to the first layer, second layer, third layer, or to the any distance. Now we will get the corresponding stress in the layer, isn't it? And we know that this is suffering from maximum compression stress, compressive stress. This is less than this layer, no, like now depending upon the distance from the neutral axis, above or below, no stress can be calculated. We can calculate the stress in the fiber, isn't it? Therefore, we are calling it as fiber stress. Y is the distance of the layer from the neutral axis in millimeter, and R is the radius of curvature the beam will bend. Now, this is the radius of curvature R. From here to here, the R from this plane to this is the radius of curvature R, isn't it? And I is the moment of inertia of the section, isn't it? Now, we know already, we have discussed about this and we have calculated, that is BDQ by 12 or DBQ by 12 depending upon the section, isn't it? That is moment of inertia in millimeter to the power of 4. Right? Now this is after derivation. Now we'll come out with this solution, isn't it? It is M by I is equal to F by Y is equal to E by R, isn't it? M by I is equal to F by Y is equal to E by R is the bending equation, isn't it? How we will get it? How we are getting it? Now this equation. Now that is in next two slides. It is available, but it is not included in our Polytechnic syllabus derivation. Therefore, I am not going to discuss about those things. Now straight away we will go to the next slides. Now this is the bending equation. Don't forget this. M by I is equal to F by Y is equal to E by R. Bending moment divided by moment of inertia, that is the fiber stress, divided by distance, that is the distance of the fiber from the neutral axis. It is the Young's modulus of the material, and R is the radius of curvature of the beam which bends. Doesn't matter. Now this bending, this is called bending equation, isn't it? It is predominantly used throughout our engineering life, isn't it? Whatever may be the design, the beam design, when beam design comes into picture, we should know about it, isn't it? If we are not supposed to forget this equation under any circumstances to become an engineer, isn't it? Either maybe a civil engineer or maybe a mechanical engineer. We want this. We should know about it, isn't it? So this is the derivation. How that equation is derived, isn't it? Very simple, no. In very simple, very simple procedure. So that anybody is interested, you please go through this and you can read and you can understand. So next, please. Yeah. Now the continuation, that is the derivation of the same thing. That is very simple. Now next, please. Yeah. Next. Yeah. See again. Now this is the conclusion. Then this is that is derivation. That is how we have derived it. Next, please. Yeah. Now in moment of resistance. Moment of resistance. Moment of moment of resistance. Now, what exactly is the meaning of moment of resistance? Doesn't it? Now, moment of resistance. See, now this is the bending moment. It is the bending moment. It is due to the application of load application. It is due to the application of load. Due to the load application, there will be bending. Now, what we need to do, that is, we have to mitigate or reduce. We have to reduce the deformation. That is our job. When you are designing the beam, it means no deformation should occur. Now, therefore, what we do, see, we have to design the section. We are creating in the opposite direction. We are creating the resistance in the opposite direction. Now, depending upon the design of this section of this beam. Now, the resistance which we are creating is moment of resistance. Now, it is there the moment induced against this force. Now, by the section. No, that is no deformation should occur. So, therefore, now what we will do? Now, we will design the section. That is, we are creating the moment of resistance in the opposite direction. Isn't it? Always the bending moment is equal to the moment of resistance. Isn't it? The moment we have to design this for this moment, that is, no deformation should take place. Therefore, you have to create the resistance in the opposite direction. Now, that resistance is called moment of resistance. Isn't it? Moment of resistance. Moment of resistance. Now, that is some examples. One example how to calculate the moment of resistance to this rectangular beam. Now, that is considering a rectangular beam breadth B and depth D. It is D by 2 neutral axis. And considering an elemental strip, elemental area. Consider the elemental area. Now, the force in that fiber, one layer, that is one fiber, that is area into stress. We know that stress is equal to load divided by cross-sectional area. Stress divided by cross-sectional area. Therefore, area into load divided by cross-sectional area. Therefore, that is load is equal to, that is force is equal to area into stress. That is in that layer, in that particular layer. And we know that this is F is equal to, that is stress. From the bending equation, M by I is equal to E by R. From the bending equation, F is equal to M by I is equal to E by R. From that equation, F is equal to this one, E by R into R by Y. Isn't it? Delta A into, that is submission. And we know the moment causing this force, this is the force in that layer. The moment causing by this force above the neutral axis is equal to force into distance. Now, this is the force into distance is the y, isn't it? Please go back. Distance in. See, force in this layer multiplied by distance is the moment due to this layer, isn't it? Now, therefore, force we have calculated. Now, this is the force I will convert this force into this form, and that force multiplied by distance, isn't it? This distance is equal to that is the simplified form of this equation, that is E by R into delta A into y square, isn't it? Now see, if you go back, now here, now we have considered one fiber, that is one layer, one fiber. Now like now this beam section consisting of number of layers, 1, 2, 3, number of fibers, 1, 2, 3, now let us calculate, that is the moment of all these layers and sum of them. Now what we are going to get it. There are, now we have considered one layer and calculated the moment about the neutral axis, isn't it? Now after doing this, now this section consisting of number of fibers, calculate the moment of all those fibers and sum of them, that what we are going to get it, we will see. Now see, that is we are going to get a sigma of this. This is the moment of one layer, which layer we have considered. Now this is the moment of all the layers, moment of resistance of, we can calculate it, moment of all the layers, so we are going to get it. Now if you go to the previous moment of inertia, there we can see sigma delta A into y square is equal to Ixx. Sigma delta A into y square, sigma, that is sigma sum of all the moment, isn't it? Moment about the neutral axis. Therefore moment is equal to E by R remains same, and this is I. Now this is the bending equation, m by bring this I this side, cross multiply, now bring this below, and we will get m by A is equal to E by R, and this is moment, isn't it? Now moment of resistance, moment of bending equation. Then modulus of section. Now modulus of section. What is modulus of section? Now here, from the bending equation, m by I is equal to f by y. M by I is equal to f by y. That is R is equal to I by y into f. Now the simplification of this, isn't it? Now just we are transferring this I to the right side. That means I by y. That we have made it I by y into f. M is equal to, that is momentum, that is moment of resistance is equal to m is equal to bending moment is equal to m is equal to I by y from the original, that is bending equation, from the bending equation. Now see, m is equal to I by y into f, isn't it? Now that is now simplification, isn't it? Now moment is equal to I by y. Now here, now this constant, now this is one I by y. Now this I by y is called modulus of section. Z is called the modulus of section. Next please. Z is the modulus of section, isn't it? Now to find the modulus of section for various sections. Now to find the modulus of one, that is for rectangular section. Now let me calculate the modulus of section for different section. This is for one rectangular section. Z is the modulus of section I by y. Is it I by y? I, we know that it is VDQ by 12, and y is equal to d by 2. That is the farthest maximum, isn't it? So therefore, it is modulus of section is equal to Z is equal to VD square by 6 for the rectangular section, isn't it? Let me calculate the one or two, three modulus of section of the different sections. See from this section modulus, Z is equal to I by y. There we can see that. Now let us consider Let us consider the rectangular section. Now, if you consider the rectangular section, breadth B and depth D. Now, this is the half of the depth, D by 2. This is the D by 2. And this is another half, it is D by 2. Now, we know that ZD is equal to, ZD is the modulus of section. ZD is the modulus of section. Now, therefore, I by Y, that is equal to I BDQ by 12, BDQ by 12 divided by, that is D by 2 of, because we know that it is suffering from maximum compression and this layer is suffering from maximum tension. Therefore, D by 2, this is the section modulus. For this beam, you please simplify this. We are going to get it, that is BD square by 6. BD square by 6. And similarly, for this circular section, Z is equal to I by Y. Z is equal to I by Y. How to calculate the I? I is pi moment of inertia about the x axis. It is equal to pi d to the power of 4 divided by 64 and the whole thing divided by, it is Y, it is D by 2, half of this. No, this is half, it is D by 2 diameter, D by 2. Farthest, either this layer or this layer, isn't it? No, therefore it is D by 2. D by 2 is the bending modulus of section for, that is circular section. And similarly, now if you want to calculate the hollow section, that is hollow portion with, so different dimension. No, if it is hollow, if you want to calculate the hollow section, no. Let me write one more. Now, if you want to calculate the modulus section for all rectangular section, see for example, now if you want to calculate it, now here, see, it is breadth B, depth D, then this is hollow portion B and D. Now, if you know here, modulus of section Z is equal to, it is I by Y. Now for this I by Y, now I is equal to, Ix is equal to, that is B D cube. It is B D cube, BD cube divided by 64 and minus B D cube by BD cube by 12. Sorry, rectangular section it is BD cube by 12, BD cube by 12 minus BD cube by 12 minus BD cube by 12. The whole thing divided by Y, it is D by 2. Farthest, it is D by 2. Farthest, it is D by 2. Now, if you simplify this, we'll get the section modulus for a hollow rectangular section. Now, this is the section. Isn't it? This is the hollow portion. Isn't it? And similarly, now we can calculate the section modulus for the hollow circular portion. Hollow circular portion. Now this is the diameter D, and for this smaller one, now it is inside. It is D. Diameter for the inside portion is D, and this is the hollow circular section. To calculate the shear section modulus for this hollow circular section, Z is equal to I by Y. It is a section modulus. Now that is equal to I is equal to, it is pi d to the power of 4 divided by 64 minus pi d to the power of 4 divided by 64, the whole thing divided by, that is y by 2. Y is equal to, it is d by 2, capital D. Now from here to here it is d by 2, d by 2. That is d by 2. That is how we can calculate the section modulus for other sections also. Is it not? And you know, see after this, now further, now see we can solve some problems that we'll solve those problems. Let us solve those problems in the next class. Thank you very much for all the participants. Thank you so much.